All right, welcome back, guys. So we left off with question 27, okay, from part 1 of the review. So I'm going to try to finish it up in this part 2. But anyway, let's get started. So number 27, this is where we would be getting into chapter 6, talking about margin of error and confidence intervals, okay? So 27, it says find the margin of error for the given values. So it gives us C, and it's 90%. And so basically we're trying to find the margin of error that would correspond to a 90% confidence interval. It gives us a standard deviation of the population and then the sample size. So you have to remember or look up in your notes this formula, okay? So Z sub C, this is our critical value, and we're going to obtain this from, you could find it using the inverse normal function in your calculator, but we've got this chart right here, and then it's sigma over the square root of n, okay? Well, basically, guys, you just plug these into the formula. So, well, first of all, if C is 90%, then our critical value is going to be 1.645 times, and sigma is 3.5, and this will be divided by the square root of 64, which is actually 8. Remember, this piece right here, this is what we call the standard error, okay? It's basically like the standard deviation of the sampling distribution, or the distribution of sample means. All right, well, I'll just plug these in the calculator real quick. So 1.645 times 3.5, and then I'm going to divide that by, well, 8, because that's the square root of 64. Okay, so this gives us a margin of error of it says round to 3 decimal places, so this 19 would actually become a 20, so this would become 0.720. All right. We'll continue. And I kind of went through here and circled the ones that I'm going to work. The rest of them are just kind of redundant. They're the same types of problems, just permutations. Okay, so that's the way 28 is. So let's go to 29. All right, so 29 here, we're actually going to construct a confidence interval. Now, guys, remember, you can construct a confidence interval once you know your margin of error. You just both add it and subtract it from whatever the sample mean is, and that will give you your confidence interval, okay? But we actually use the calculator. We let the calculator do all that for us. So it says a random sample of 45 home theater systems has a mean price of $118. And then we're going to assume that the population standard deviation is $18.50. So we'll construct both a 90 and a 95% confidence interval. So to do this, you go to Stat, you go to, let's see, Tests, and you come down here to Z interval, okay? You hit Enter. And we're using the statistics, so come over here, make sure you hit enter there. And then the population standard deviation is 18.5. The sample mean is $118. The size of the sample is 45. And then our level of confidence is 90%, so 0.9. Okay, and you just calculate. And that's it right there, guys. Okay, it's going to go from, this says round to 2 decimal places. The calculator gives you the interval accurate to 2 decimal places. So this would be your lower bound, and then this over here would be your upper bound. And then you just do the same thing for a 95% confidence interval. Okay, so go here to stat again, go to tests and down to z-interval. The only thing I'm going to change is my level of confidence. Change it from 0.90 to 0.95. And now, this is my new confidence interval. And what you will notice, guys, is that this interval is actually a little bit wider. Okay? And that's actually what they want you to realize in this part. It says, sorry about that, it froze on me again. Let's see. I think it's going to be B. It says, with 90% confidence, it can be said that the population mean price lies in the first interval, okay, within this first interval that we found. And then with 95% confidence, it can be said that the population mean price lies in the second interval. And then the 95% confidence interval is wider than the 90%. It has to be wider, guys, because we're trying to use a higher level of certainty. Okay, so anyway, I hope this doesn't keep freezing on me. All right, well, number 30 is pretty much the same. You'll be finding a confidence interval using the z-interval. Okay, 31 is the same thing. And then 32 is a bit different because here we're still finding a confidence interval. However, a standard deviation of the population is not given. And so this would come from section 6.2. So when we don't actually know the standard deviation of the population, we use the standard deviation of the sample as an estimate. And consequently, there is more uncertainty involved. And so we end up getting a wider confidence interval because that corresponds to this t-distribution. So if you remember, the t-distribution was wider and it had fatter tails, okay? And it also depended on what we term the number of degrees of freedom, okay? Or in other words, the size of the sample. But for this one, we can do it the same way using the calculator, except you're not going to use z-interval. You're going to come over here to test, and you're going to come down and use t-interval, okay? Now again, you could do this one by hand. You'd have to find the margin of error again, and that would come from a critical t-score. And so you would have to use a t-table to figure that out. Or you could use that inverse t function in the calculator. All right, well, let's plug these in. So x bar, the sample mean, is 14.8. The sample standard deviation is 2. And then the size of the sample is 8, and we want a 99% confidence interval, okay? So come down here, calculate. And it says round to 1 decimal place, so this would go from 12.3 to 17.3. So 12.3 to 17.3. Okay. Number 33 is exactly the same. 34, however, we're still constructing a confidence interval. However, the first thing that it wants you to do is identify the margin of error. Okay. So it says in a random sample of 10 cell phones, the mean full retail price was $520.50 with a standard deviation of 224. So again, we're going to be relying on that t-distribution because we don't know what the standard deviation of the actual population is. It says assume that the population is normally distributed and use the t-distribution to find the margin of error and construct a 99% confidence interval. Okay, so the margin of error is really found the same way, guys, except instead of z sub t, kind of said that backwards. Instead of z sub c, it's t of c, okay, where t is your critical t value. And then you're not going to be using sigma, though. You can be using s over the square root of n, okay? All right, so unfortunately, I thought they would have done this, but they did not provide a chart here. So you could do a search, guys, for a t-table or critical t-scores, or you can use this inverse. Let's see. No, it's under distributions. Yeah, this inverse t function right here, okay? And so it'll give us the critical t-score if we give it the area that's to the left of whatever this critical t-score is. Well, this critical t-score basically encapsulates 99% of the area under the curve. So that means the two tails have 0.5% in each one. So in other words, let me draw you a little picture. You remember, like, technically there's a negative one over here, and then over here there's a positive one because this is symmetric. But between these two, we've got 99% of the distribution. So in order to figure out this t sub c, or this critical t-score, we've got to put in the area that's to the left of it. Well, if I have 0.5% in each tail, then I would have this 99% plus this 0.5%. So that would be 99.5%. So the area that's to the left of the critical t value that I'm looking for has 0.995 area to the left of it, okay? And then the degrees of freedom, let's see here. This is a sample of 10 cell phones, okay? So I put a 10 in there. I can paste this in, and that is my critical t-score. So the margin of error is going to be equal to, let me round this to 3 decimal places, 3.169 times the population, or excuse me, the sample standard deviation over the square root of the sample size, okay? So you can type all this in your calculator, guys. I already got that t value in there, so I'm just going to say times the 224, and I'm going to divide that by the square root of 10. That'll be my margin of error. So to 1 decimal place, it's going to be 224.5. Okay. That's a big margin, relatively large margin there, and part of the reason is because standard deviation of the sample is really large, and furthermore, the size of the sample is relatively small. Now, once you know this, you could find these lower and upper bounds of this confidence interval. Just take this sample mean and both add and subtract this margin of error from it. But again, the easiest way to do it is going to be doing a t interval, okay? So I'll do that for you again real quick. Oops. Okay, so sample mean is 520.5. Sample standard deviation is $224. Size of the sample is 10. And this is a 99% confidence interval. And so these are our bounds, guys. It says round to 1 decimal place, so it'll be 290.3 to 7. Well, I'll go ahead and write these down. to 750.7. Okay. Now, to interpret our results, let's look at this. Well, what this means is that 99% of the time, each time you take a sample, or if you were to take 100 samples, 99% of those samples will contain, or 99% of those confidence intervals built around each of those sample means will encapsulate the true population mean. Okay, that's literally what this means. So let's look and see here. I think that it's A. I'm going to double check this though. This one's 34. Well, it says that it's B. It says with 99% confidence, it can be said that the population mean full retail price. Okay, well, so just remember that it should be B. All right. Oh, well, and up here for part one, this is actually in dollars, guys, the unit. Okay, so don't forget about that. Oh, this is kind of weird because I print this off and save it as a PDF, so that's why when you guys are doing this in the software, I'm sure this will follow the first part of the question. All right, 35 is exactly the same. The only difference is you need to find the mean and the standard deviation first, and then construct your, in this case, 95% confidence interval. So let me give you a tip. I did this in the lecture on 6.2. If you go to do a t-interval, instead of using stats, come over here and click on data, and then make sure wherever you put the data, whatever list you put that data in, make sure this is the list that you're referencing. And so the nice thing about that is that the calculator, it'll go ahead and calculate the mean and the standard deviation for you, okay? And then it'll construct this confidence interval. All right, 36. It says in a sample of 13 randomly selected high school seniors, the mean score on a standardized test was 1,191, and the standard deviation was 168.6. It says further research suggests that the population mean score on this test for high school seniors is 1,010. Does the t-value for the original sample fall within what this means is a 95% confidence interval? Okay. And it looks like it's asking you okay. Yeah, I had to think about this one for just a second. First of all, we need to find the t-value that corresponds to this sample mean. Okay, so to do that, it's going to be x bar minus mu, very similar to finding the z-score, but this will be over s. Wait a second, hold on just a minute. Okay, yeah, I was on the right track. I'm just kind of confusing myself. Yeah, so you're going to get your t-value by using this. Remember, we don't know the population standard deviation, okay? So x bar is 1191 minus the actual mean of the population is 1010, and then this is over the sample standard deviation, which is 168.6, and then that's divided by the square root of 13, because that's the sample size. So first we're going to have to find this this t-value. And I'm going to divide this by that denominator, which I'm keeping in parentheses, square root of 13. Okay, so to 2 decimal places, this looks to be 3.87. This is one reason I wanted to do this one. So now to actually know whether it falls within a 95% confidence interval, we need to find that confidence interval, okay? Or, well, let me think just for a minute here. No, we just need to figure out that critical t-value that's associated with a 95% confidence interval, okay? So in other words, you know, if you think about that t-distribution looks like, we just need to find this t-value such that there's 95% in between the negative and the positive t-value, but also an extra 2.5% in this left tail, okay? So that's a total of 97.5%. So I can use my inverse t function, but the area that's to the left of this critical t-score, the t-value, is going to be 97.5%. All right, so let's come over here and get it. The inverse t, so 97.5 or 0.975. And then the number of degrees of freedom is 13 for this one. So this will give us that critical t. So let's see, to 2 decimal places, this one is 2.16. Okay, but this first value, or the associated t value that's associated with this sample mean, it falls outside. It would fall outside of our 95% confidence interval because this value is greater than this critical t value here, okay? So we're going to say does not fall between, this just means fall within a 95% confidence interval, okay? Guys, this is really the same thing when you did that hypothesis testing. You standardized your sample mean, and it was a z-score. And if it was greater than your critical z-score, then you would, well, no, it's not exactly the same either. I take that back. Yeah, because this is just strictly going to be outside of this confidence interval. All right, well, let's go to 37, if I haven't thoroughly confused you. So here at 37, guys, this deals with section 6.3 when we were trying to find confidence intervals for population proportions. Okay, so not a mean, but rather a proportion. And it says in a survey of 2,741 adults, 1,428 say they have started paying bills online in the last year. So we want to construct a 99% confidence interval for the population proportion, okay? All right, now to actually figure out our sample proportion, p hat, if you recall, it's actually the proportion of respondents that said yes, essentially, over the total, okay? And this is always a decimal, so let's see what this is. Okay, well, it doesn't actually ask us for p hat. I'll just write 0.523, okay, roughly equal to 0.523. But to actually find the confidence interval yourself, guys, you can go to the calculator again, go to tests, and do this one right here, 1 proportion z-test. Okay. Oh, no, I'm sorry. Now we got to go to distributions again. Hold on a minute. Now here it is, okay. Here it is, it's 1 proportion z-test. That's the one you want. Okay, and you're going to put in there x is just the number of respondents that affirm, okay, essentially. So you can just type in 1,428. So the calculator will calculate p hat for you. And then I don't know if you recall or not, but you can find, once you know p hat, you can find q hat. And once you know that, you can find the actual standard deviation, okay? But fortunately, the calculator will do all of this for us. We'll just put in the sample size to 2,741. We want a 99% confidence interval, which I've already got that in here. Hit enter, and this would give it to us, okay? So to 3 decimal places, this would be 0.496. And then the upper bound would be 0.546. Be careful with your rounding, guys, because, you know, if you just round that last digit incorrectly, then you would get this wrong. All right, so let's interpret these results. This one is going to be A. Okay. It says with 99% confidence, again using that same terminology from above, it can be said that the population proportion of adults who say they have started paying bills online in the last year is between the endpoints of the given confidence interval, which is right here. So somewhere between 49.6 and 54.6. All right, well, let's continue. Number 38 is exactly the same. Let's go to number 39. Oops. Okay, so number 39, it says a researcher wishes to estimate with 95% confidence the population proportion of likely U.S. voters who think Congress is doing a good or excellent job. And her estimate must be accurate within 2% of the true proportion. Okay? It says no preliminary estimate is available, and what we want to do is find the minimum sample size needed. So guys, there's a formula for that. If you look back in your notes, it's right here, okay? And furthermore, if an initial estimate is not given, then you use 0.5 for your point estimate, okay, for your p hat. Now remember, q hat is the proportion of individuals, or whatever the case may be, that don't correspond to. It's sort of like successes and failures. Okay, we were talking about binomial distribution. So if 50% of people pay their bills online, then that means 50% of the other people do not. Okay. So anyway, this is the formula that we have to use to figure out that minimum sample size. So let me, oops. Write this in the notes here. Okay, so n is equal to p hat times q hat over z of c over the margin of error, and all of this is squared. Okay. Yeah, so anyway, so we're going to be using 0.5 for both p hat and q hat. And then z sub c, you have to remember those critical z values. So for a 95% confidence interval, here's in the table up here. And you can see it's right here. The critical z-score is 1.96 for a 95% confidence interval. So that's what I'm going to use. All right, so I'm just going to plug in all these values. So 0.5 times 0.5 times, in parentheses, 1.96 over, and then the margin of error, they don't want a margin of error any greater than 2%. Okay, so 2% is a decimal, is 0.02, and then you square all that. You can plug all this into your calculator. And on these guys, you always have to round up, because you can't have a fraction of a person, okay, or a fraction of a instance of sampling. All right, well, 0.5 times 0.5 is 0.25, okay, times, and I'll put all this other stuff in parentheses, 1.96 divided by the margin of error. And I'll square that, and this should give us, well, it comes out to an even number. So 2,401. So that is the minimum sample size needed if you don't have a previous estimate, okay? But now this says, what is the minimum sample size needed using the results from a prior study that found that 26% of the respondents said that they think Congress is doing a good or excellent job. So now we have a value for p hat, 0.26. So if p hat is 26%, that would make q hat 74%, okay? And then all this other stuff would be the same. And this is going to result in a smaller sample size as well, because we have something with which to start, okay? We basically have more information than we did in that previous case. And square that. Okay, so now if I round this up, this is in fact a smaller sample size. It's 1,848. Okay. And then as far as interpreting our results, having an estimate of the population proportion. No, it doesn't raise the minimum sample size, it actually reduces it. Okay, so I think it's going to be B. All right, now let's keep going. Number 40 is just like it, guys. So is number 41. Okay, well, now we're going to come to number 42. So this will take us into chapter 7. So this should be the freshest because you guys submitted those statistics projects not that long ago, and you had to do some hypothesis testing. Okay, so it says a null and alternative hypothesis are given, so it's right here. Determine whether the hypothesis test would be left-tailed, right-tailed, or two-tailed. Interestingly, here though, guys, the hypothesis test is not concerning the mean or the average. It's actually concerning the standard deviation, which is interesting. But in any case, to determine the type of tail test, it's a bit of a tongue twister there, it's going to be, you look at the alternative hypothesis. Okay, so if it says that sigma is greater than 2.1, you'd be using a right tail test, because your test statistic would have to fall very far to the right in that right tail in order for you to be able to reject this null hypothesis that the sigma is actually less than or equal to 2.1. All right, 43 is the same. Okay, we'll go to 44. And these are kind of weird the way they have them laid out here, but in any case, it says your medical research team is investigating the mean cost of a 30-day supply of a certain heart medication. A pharmaceutical company thinks that the mean cost is more than $95. You want to support this claim, so how would you write the null and alternative hypothesis? Well, guys, you got to remember that the equality part is contained in your null hypothesis. So the claim is that the mean cost is strictly more than. Okay, so it would be that mu, my alternative would be that mu is strictly greater than $95, and my null hypothesis would be that mu is actually less than or equal to $95. Okay, so you just have to find which one corresponds to what I just wrote down. Okay, I think it's going to be this one for part 1, and then this one, okay, for part 2 there. All right, well, 45 again is the same. So let's go to 46. So 46, we're actually going to be doing some hypothesis testing. It says, test the claim about the population mean, mu, at the given level of significance using the given sample statistics. Okay. So the claim is that mu is equal to 50, and then it gives us the standard deviation. Oh no, this is alpha. This is the level of significance. Then it gives us the standard deviation of the population, and then the sample mean and the size of the sample. Okay. So if the claim is that mu is equal to 50, that's going to be our null hypothesis. So which choice would that be? Which would mean the alternative hypothesis is that mu is not equal to 50. So guys, that's going to have to be choice E. That's the only one that will work. And then it says, calculate the standardized test statistic. Okay. All right. So that test statistic, this corresponds, well, if alpha is 4%, and that means this is like, corresponds to point, well, no, let me not write it like that. Yeah, I'll just write z sub alpha, okay? This is going to be x bar minus the mean over standard deviation divided by the sample size. So you're just going to plug these in. I'll just do this in my calculator. So x bar is 48.1 minus, remember, mu is the hypothesized mean because we don't actually know what the mean is. 50. Hit enter, and we'll divide this by standard deviation is 3.42. And divide that by the square root of the sample size, which is 63. And this gives us, well, this negative 4 point, it says round to 2 decimal places, negative 4.41. That's actually pretty far from the mean. And then it says determine the critical values. Okay. Well, all right, so what I'm going to do is, this is a right-tailed test. Oh, wait, no, it's a two-tailed test, I'm sorry. It's a two-tailed test. And so what we're trying to figure out, these critical values, going to be, this is your positive, and this one over here is your negative. You just need to find one of them because they're symmetric, but we've got 0.96% of the distribution between these two, okay? And so this means that I'd have 2% and 2% in each of these tails. 0.02 and 0.02. So you can find either the left one or the right one. It doesn't matter. You can use that inverse normal function, but you got to put the area that's to the left. Okay. So I think in class I just showed you to find the negative one because the area to the left is easier to find. So it's just 0.02. And then this, because we're looking for z, the mean and the standard deviation are 0 and 1 respectively. Hit enter. And you get negative, let's see, to 2 decimal places, this would be negative 2.05. So the critical values are both the positive and the negative 2.05, okay? The negative's right here and the positive is over here. So if our standardized test statistic falls either below this one or above this one, then we reject the null hypothesis, okay? And that's actually what we're going to do because this negative 4.41 would be way to the left of negative 2.05 right here. So we're going to reject H naught. And that is actually the claim, okay? I'm going to go with C. It says reject H naught. It says at the 4% significance level, there's not enough evidence to support the claim. Because the claim is our null hypothesis, okay? I'm going to check this one real quick, guys. Just want to make sure. Oh, this one's number 46. Well, it says it's A. Okay. It says reject H naught at the 4% significance level. Oh, yeah, there is enough evidence to reject the claim. Yeah, I was saying it backwards. Okay, this is similar to, when you assume somebody's innocent in the judicial system, and you find enough evidence, and then you no longer assume that they're innocent anymore. Okay, so you reject that supposition that they're innocent, and you say that there's essentially enough evidence to assume that they're guilty. All right, so be careful with the wording on some of these. There is enough evidence to reject the claim. Okay. All right, 47. I think 47 is similar to the last one, guys, but I wanted to do 47 because we're still finding the standardized test statistic, but we're finding a p-value, okay, in this one. So, let's see. The claim is that mu is greater than or equal to 1474. So this will have to correspond to the null hypothesis. So it's got to be choice C, okay? And then calculate the standardized test statistic. Well, here again, you're going to use that same formula. And we'll do this real quick. So the sample mean is 1467 minus the hypothesized mean, which is 1474. And we're going to divide this by the standard deviation, which is 28, divided by the square root of the sample size, which is 26. Okay. Enter. So this is our standardized test statistic. It's negative 2 decimal places, negative 1.27. All right. This would be a left-tailed test if you look at the alternative hypothesis. Okay. And so the p-value is basically the area is to the left of 1.27. Okay. This area right here. So that's what we've got to find. So to do this, we can, let's see, here to, well, no, go to distributions and go to normal CDF. Okay. And our lower bound can be negative 1 or negative infinity. And then our upper bound will be this z-score, negative 1.27. And this will give us the area, okay, is to the left of this critical z-score. And that area is related to p. Remember, this is the probability of rejecting the null hypothesis when it's actually true. So it's similar to convicting someone when they're actually innocent. And so you want that probability to be as low as possible because you don't want to convict an innocent person. All right, well, this comes up to about, it says around to 3 decimal places, 0.102. Okay. Now, to determine whether we reject the null hypothesis or not, we would compare the p-value with alpha. Okay. So, well, the p-value is greater than alpha. Okay, because alpha is 5%. So if the p-value is greater than alpha, then we fail to reject H0. At the 5% significance level, there is not enough evidence to reject the claim. Okay. All right. Okay, 48 is just like the last one. So is 49. See, find the standardized test statistic and then the p-value and then figure out what to do. And so is 50. All right, so now we get to 51. And this would take us into chapter 9, okay, when we were talking about correlation and linear regression. So it says the scatter plot of a paired data set is shown here. Determine whether there is a perfect positive linear correlation, a strong positive linear correlation, a perfect negative linear correlation, etc. Well, this is not perfect because it doesn't form a straight line. However, it is very strong. It is a strong positive linear correlation. Okay. In other words, the slope is positive. Okay. This just means that as values of this independent variable x here tend to increase, so too do the values of this second variable y. Let's see. 52. I was going to skip this one, guys, but there is no correlation. Because see, there is correlation, but we don't cover it in this class. There's no linear correlation, and that's what they're asking you about. Now, not because this looks like a parabola, doesn't it? All right, let's keep going. We're getting there. Okay, we don't like too much. Now let's see. We got. I'm going to pick out. They include the chart. So we got 53, 55, 56. Well, that's it. Okay, so we're almost there. All right, so 53. So it says the accompanying table shows the ages in years of 11 children and the number of words in their vocabulary. And so first thing we want to do is find the scatter plot. Okay. Well, guys, unfortunately, the data for me is on another page here. So what you would do is just look at your chart and then look at where your ordered pairs are. Okay. My guess is that it's either going to be C or D because there's a positive correlation here with a child's age and their corresponding vocabulary size. So it's either C or D. I don't know which because I'm not going to take the time to. Well, actually, I can tell you it's C because the age is going to be the independent variable. If you look down here, see that? And then y is the dependent variable, the vocabulary size. So D has the x-axis labeled incorrectly. All right, and then the sample correlation coefficient. So for this, what we'll actually do is input this data into our calculator. And I should have done this before. So maybe I'll pause real quick. Okay, guys, I just got finished. I put values for x in list 1, and I put values for y in list 2 because I don't have or in list 3 rather. Okay, and so now I'll come back up here. I'm trying to find R, the correlation coefficient. So I'll quit this screen and we'll go over here to stat and calculate. And we're going to go to this linear regression, number 4. And I'm using list 1 for my x's, but I'm using list 3 for my y. So list 3 is right here in blue. And just hit calculate. Now remember, if this pops up and it doesn't actually give you R, it's because you have your statistical diagnostic tool turned off in your calculator. So what I have to do is come down here to the catalog and go down to the D's for diagnostic and just click enter. Okay, click enter again. Now go back to stat and just do the same thing. So now, along with A and B, which is basically the slope and the y-intercept, it'll also give us that correlation coefficient. Okay, so to 30 decimal places, this would be 0.9976. And then as far as there is a, let's see. Okay. There is blank linear correlation. Very strong positive linear correlation, what I would say, but I'm not seeing that. Must be way down here. Okay, see here, a strong positive, that's what it should be. And then for this part, as age increases, the number of words in a child's vocabulary tends to increase, so it's going to be C. And then for part D, we want to determine is this significant, okay? So the critical value is, so what we have to do is look at that Pearson correlation coefficient chart, okay? And the significance level is 1%, or alpha is 0.1. So let's come down here and look at this. Well, here it is in this column. Our sample size, well, I think it was 12, if I'm not mistaken. Let me look back here at my list. Oh no, it's 11. Sample size is 11. All right, so at the significance level of 1%, sample size of 11, this right here is our critical value, 0.735. Okay, so the critical value is 0.735. Therefore, there is sufficient evidence at the 1% level of significance to conclude that part 3, let me see what my choices are. Oh, there is a significant linear correlation. Yeah, that's the one we want. Okay. Yeah. I don't know why it says round to 3 decimal places. It must be for anyway. All right. Well, 54 is just like it. Okay. Of course, it gives you the chart to reference again. Let's look at 55, okay? So it says, so what we have here is a scatter plot, okay? It looks like there is a trend in this data. It says years of experience and then the annual salary, and this pertains to registered nurses. So it looks like as the number of years of experience increase, so too does the salary up to a point, okay? It looks like beyond about 18 or 20 years, this trend doesn't actually continue. And that's kind of the downside to using models to predict. If you're going to use a model, you need to make sure that your predictions are within, the domain. But anyway, it says an analyst used the regression line for the data to the right to predict the annual salary for a registered nurse with 28 years of experience. And then the question is, would this be a valid prediction? And I'm going to say no, because 28 would be way over here. The trend kind of falls or stops right here, guys. Okay, this is a pretty accurate, this would be a pretty accurate model for predicting the salary of a registered nurse given his or her number of years of experience up to about 18 or 20. after that, it looks like this model kind of falls apart. So for this one, I'm going to go with C. It says no, the prediction is not meaningful because 28 is outside the range of the original data set. I'm pretty sure that one's C, but I want to just double check this one as well. Number 55. Okay, yeah, it is C. Okay. All right, well, I think that I had picked out one more. Yeah, it's this one right here, okay? So what we're doing here, guys, is we're actually going to do a linear regression and find a regression line, okay? So the same thing, you're just going to put this data in for X and for Y, list 1, list 2, whatever the case may be. And you're going to go to linear regression and it'll generate those values for you, okay? So let me pause and put in this data. Okay, well, I've got my data in here, okay? So now I'm going to go to Stat, and then to Calculate, and down to number 4 for linear regression. And I'm using those same two lists, okay? So make sure you don't get your lists backwards. So when I do this, this now will generate these coefficients, okay? So y hat, or the predicted value, is going to be A is your slope. It goes in front of the x, and then B is your y-intercept. Okay, that goes in front of, or that's your constant basically. So the 3 decimal places, this would be 21.621. And then the value of A to 3 decimal places will be 0.039. Okay. And then the rest of this, guys, is pretty much, well, you pick out the scatter plot. Okay. It's not going to be C or D because there's a positive correlation here to the height of a building and the number of stories that building has. So it's either going to be, well, you could just probably look here. It looks like it's going to be A. And the reason I know that is because that's where the y-intercept is. Up here it's around 30. And then the rest of this, you're just using this equation right here to predict these values. Okay. So I'll go ahead and do this first one. When x is 501, you just plug that in right here, okay, using your calculator. So you'll say 0.039 times the value for x, which is 501, plus the 21.621. You hit enter. This will be the predicted number of stories for a building that has a height of 501. So you'll round to the nearest you'll round to the nearest story. Okay, so 41 here. Okay, and you'll do that for most of these. Now, the only one you're going to want to be careful with is maybe this one right here, because this value of x is not really within this data set. See, this kind of ranges from the 500s, or well, starts at the latter 400s and goes through the 700s. So really, any values of x outside of that range, they may not yield accurate predictions. Okay, so I bet you if we were to look at the answer here for part C, it would be not meaningful. We can actually do that real quick. Yeah, see, For part D, it says not meaningful, okay? All right, guys, well, I know this was kind of on the fly, but I hope you'll be able to gain some benefit from it. Like I said, a lot of these questions are duplicates, and the reason behind that is that is just really to prepare you for the final, okay? The final's not going to have that many questions. But in any case, I hope you do well on it, and let me know if you have any questions.